ተመልካቾቻችን የዊትስቶን ብሪጅ ኤሌክትሪካል ሰርኪዩት አናሊሲስን ሰውየው በአግባቡ ያስረዳል። በጥሞና ተከታተሉት። እናመሰግናለን።
What's a wheatstone's bridge, you ask? Well, here's an example. Wheatstone's bridge is a circuit that contains 4 resistors like these, and we call them the 4 arms of the bridge, and there is a resistor in between like this. So this is a Wheatstone's bridge. Now before I continue, let me ask you, what if I ask you to calculate the current through this circuit? How would you do that? Well, if you ask me, the first thing I always like to do, or I always like to think about, is can I reduce this circuit into a single resistance by using my series and parallel formula? Can I do that? Well, I don't see any resistors in series. These are not in series, there is a resistance in between. I don't see any of them in parallel. Again, they are not in parallel because they're not directly connected across each other. So I can't reduce this using series and parallel. And when I can't do that, the next thing I resort to, the general method, is Kirchhoff's laws. But of course, Kirchhoff's law is tedious. You know, I have to think about currents and then I have to use the loop rule and blah. But here we won't require Kirchhoff's laws because this is not any Wheatstone's bridge. This is a very special Wheatstone's bridge. What's the speciality, you ask? Well, you can see that the resistors here are having the same ratio as the resistors here. 1:2, 1:2. Or you can also say resistors here are in the same ratio as resistors here. 1:5, 1:5. And whenever you have a Wheatstone network like this, where the ratios are the same, then we say such a network is balanced, such a bridge. We call it a Wheatstone's network or a bridge or a circuit, same thing. We call that a balanced network. You may ask, okay, that's a nice thing, but why should I care about a balanced Wheatstone network? Why should I even care about a Wheatstone's network? We'll come to that slowly. We'll see the practical application. But the speciality of a balanced network is that it turns out, and we will see how, that's the whole idea behind the video, to logically see how, it turns out that whenever this network is balanced, there will be no current flowing through this middle resistor. So in this case, the current over here becomes 0. And if the current here becomes 0, that means the current here should be exactly the same as the current here. All the current from here flows here because nothing flows down or nothing flows up. And so that means these two come in series. Similarly, these two also come in series, same current flowing through them. So you see, in the balanced condition, it's as if this resistor was not even connected. So I can completely neglect that resistor and my circuit will not be affected. And the beauty now is that means I can now solve this series, parallel, and I can solve this. And so often in your problems, you'll be given Wheatstone's network like this, and you may have to identify whether it's balanced or not. If it's balanced, then it's your lucky day because then you can solve it immediately. So before we go forward, let's do a quick check of our understanding. Here are 2 networks. I want you to pause the video and see if they are balanced or not. All right, let's look at the first one. This is a Wheatstone's network, very similar to this. I've just arranged them a little differently. And this is usually how the Wheatstone's network is shown. And let's see if it's balanced. Well, this is in the ratio 1:3. This is in the ratio 3:1. You see that? 1:3, 3:1. So this is not a balanced network. So here current will flow. And so if this network was given to you, bad day for you. Okay, if this was 10 and this was 30, then it would be balanced. What about this one? Well, it looks like it's a balanced network, 1:4, 1:4. But if you look carefully, you will notice something's wrong here. This is not even a Wheatstone's network. Notice, Wheatstone network is connected between, the red resistor is connected between these 2 points. This and this point is here now. Can you see that? Because this is where the battery will be connected. I've just like rotated this. So don't get confused. This is not even a Wheatstone's network, and you can directly solve this. You know, these are in series, these are in series, the 3 are in parallel. So don't get confused. Definitely resistor current here won't be 0 because it's not a Wheatstone's bridge. On the other hand, if this resistor was connected here, then it would have been a Wheatstone's bridge. And now we can check the ratios 1:3, 1:3. Now the current over here would be 0. So now let's get back to the point. Why is the current over here 0? How can we logically understand this? You see, in the books, they derive it using Kirchhoff's laws and everything, but I always wondered, why if it's a balanced condition, why if the ratios are the same, why would the current be zero? Well, here's how I like to think about it. First, I would like to make a copy of this circuit without that red resistor and see how the voltages get distributed everywhere. That will give us the clue. All right. So in this particular case, current is running and everything. Over here, notice now these two resistors are in series. Similarly, these two resistors are also in series. And you know, in series, current is exactly the same. So from Ohm's law, because I want to talk about voltage, I'm going to go to Ohm's law. Ohm's law tells me that V equals IR, V equals IR. And so if you have two resistors which have the same current, then notice the voltage must be proportional to the resistance. In other words, if the ratio of resistance here is 1:2, the ratio of voltage here must also be 1:2. So if the voltage here is X, the voltage here must be 2X. Same is the case here. If the voltage here is X, the voltage over here must also be 2X. And that means I can now immediately calculate what the voltage is, because I know 9 has to be divided in the ratio 1:2. And when you divide that into 1:2, you get 3 and 6. And that's why I took 9, because it's easy to divide that. But you couldn't take, you could have taken any values of the voltage. And the same will be over here. Here also, this would be divided in the 1:3 ratio, 3 volts and 6 volts. So voltages get divided equally because the ratios are the same. So what? What does that do? Well, now let's look at the voltages at these 2 points. To do that, remember, whatever is the voltage here, same is the voltage here. So the voltage here and here is exactly the same, isn't it? If you want to call that as 9 and you want to call this as 0, then this would be 9 and this would be 9 as well. Now notice when I go from here to here, there's a 3 volt drop. But when I go from here to here, there's again a 3 volt drop, meaning these 2 points must also have the same voltage. So voltage at point A must exactly equal voltage at point B. That's the consequence of having the same ratios of the resistance. So what, you ask? Well, now notice, because the voltages are exactly the same over here, if I were to go ahead and now in this circuit, when it's running, if I were to put a resistor in between or a capacitor in between, doesn't matter what you put in between, notice the voltage across it is the same. Therefore, these two voltages are the same. Therefore, the potential difference is 0. There is no difference in voltage. There is no potential difference, and therefore there will be no current flowing over here. And that's why a balanced Wheatstone's network has no current. Does that make sense? Isn't that wonderful? The whole idea is when the ratio of the resistances are the same, the voltage also gets divided in the same resistance, and therefore these 2 points will end up with the same voltage, making sure there is no potential difference. That's why the current goes to 0. And now hopefully you'll agree that it doesn't matter what voltage you put over here, what are the values of the resistances over here or over here. All that matters is that the ratio here must be exactly the same as the ratio over here, and then you'll find no current flowing in between. Now you might ask, okay, so what's the application of this? Why should I care about this? Well, this network is used in calculating practically values of unknown resistors. For example, let's say there is a wire over here, or there's some object over here whose resistance we don't know and we want to calculate it. What we can now do is we can set up a Wheatstone's network like this, and instead of a red resistor over here, we can put a galvanometer. A galvanometer basically detects current. It will tell you if there's a current here or not. And then we can take one of these resistors as a variable resistor, something that's resistance can be changed. And now all you have to do is keep changing this resistance and look at the value of the galvanometer. So as you keep changing this resistance, let's say the galvanometer becomes, the value becomes 0 when you hit, I don't know, maybe 7 ohms. When this goes to 7 ohms, let's say the current over here goes to 0. Now I know, aha, this Wheatstone network is balanced. Therefore, the resistance here must be exactly, the ratio here must be exactly the ratio here. And since this is 1:7, this must be 1:7. So the resistance over here is 7 times 5, 35 ohms. Amazing, right? So you can use this, and we will use this in a future video called Meter Bridge to explore how to use Wheatstone's network in practice to calculate unknown resistance. Now we could stop over here, but I want to go one step forward and generalize this, something that might help you in your competitive exams. So let me bring back the original circuit. My question to you is, do you think that this circuit can be extended? Let's say I add more resistances over here. Something like this. What do you think about this one? Would this also be balanced? It's a more complicated circuit now, but would it be balanced? Would the current here and here be also 0? Can you pause and think a little bit about this? All right, let's see. We can apply the same logic. The first step is to first neglect the resistances and then see how the voltage gets divided. Now notice that the ratios of the resistances here is exactly the same as over here, 1:2:5, 1:2:5, which means the voltages will also get divided similarly, right? 1:2:5, 1:2:5. And therefore, the voltage drops will be the same, just like before. And that means the voltages here must be the same as here. Voltages here must be the same as over here. In other words, there will be no current flowing over here, which means you can solve the same circuit here as well. Beautiful, right? Extended Wheatstone's network, something you might see in JEE. Let me show you another way in which we can extend this circuit. What if we extend the circuit this way? What do you think about it now? Again, pause the video. I know it looks very complicated, but pause the video and think a little bit about it. The batteries are connected across this and this. All right. Again, notice we can use the same logic. If you forget about these resistors in between, then the voltage should get divided equally because, again, they have the same ratio, 1:2, 1:2, 1:2. And therefore, the voltages here, here, and here must be the same, so no current will flow over here. And so you can neglect this and you can solve this circuit. If I hadn't given you the color coding, just look at how complex this looks like. Typical, competitive exams problem. Looks very complex, but by using the same logic of Wheatstone's network, you can.
ተመልካቾቻችን ይህንን ቪዲዮ ከወደዳችሁት ላይክ፣ ሼር እና ኮሜንት በማድረግ እንዲሁም የተለያዩ ቪዲዮዎች እንዲደርሷችሁ ሰብስክራይብ በማድረግ እኛን